Oh, Brandon, you might know anybody who's selling a truck, let me know. I'm trying to buy it.
Freddie probably won't be able to afford it.
What's that?
Freddie probably won't be able to afford it.
Yeah, I'm pretty sure that's true. I heard that he almost traded his car in the other day for a boat.
Yeah. He doesn't even want to. When did it
He flip-flops more than anybody I know about stuff.
So when you start fixing headings on the video, like
What headings?
Modern physics.
I'm kind of.
Oh, I haven't changed it. Yeah, sorry, I just keep changing the template. Modern. I'd write in white. Look, I can see. All right, so next time, where do we finish off? We got our Lorentz transformations, and let's see, how far do we get?
They can help with math.
You like flew by length contraction.
Yes, length contraction. Okay, so let's go ahead and talk about that for a second. Shoot, I thought I had the last time chance to do, but I didn't. So I'll have to use the book. All right, so does everybody have their book today?
Yeah.
Okay. You don't need to write this second, but we will need it later because I'm not going to spend my time recreating all of these graphs. It's going to be a nightmare.
I'm not going to look through something.
Okay, length contraction. What is going on with length contraction? All right, the idea of, well, let's actually start with time dilation. Time dilation, we came up with this equation that says delta T. All right, now where did that come from? Really, that's just a simplification of 213b. 213b is telling us that we've got T is going to be equal to gamma b times our b over c squared x equals t. Now, the idea of this is anytime that you can take two events that happen at the same location. Now, the easiest way to do this, and the most often this happens, is when you are the location. Okay, so if you sit there and say, the next thing I know, this event happened here. Okay, and what you want to do is think about yourself as the location and think about your surroundings moving past you. So this was the muon example. Did everybody get through that example? Please, maybe.
What number was that?
Example 2.2, I do believe.
Maybe.
I look.
It was on your homework.
I spent about 10 minutes on it.
All right, anyways, we'll talk about the muon that actually gets down to Earth and how, from the muon's point of view, it's length contraction, and from the Earth's observer's point of view, it's time dilation. All right, the point being is that from the muon's point of view, okay, that its position is its own location, so it doesn't change. So if I want to see T2 minus T1, and we showed how this can be written inside here. If the position doesn't change, this just goes away. This whole section right here becomes 0 and goes away, and we end up with a nice happy equation. Change in T is equal to gamma V, change in T prime. Now, it's one thing that does kind of matter for this is we want to not necessarily say change in T prime, because as of right now, we've had the situation that the S prime coordinate we're referencing is the one that's moving. Okay, that isn't necessarily universally true. So what we want to say instead is we're looking at this as change in T0. Okay, T0 is now the location, and we're going to have L0 here in a second. T0 represents, the subscript 0 represents the reference frame where the object is not moving, okay, where everything is moving past it, where the locations, the events, are happening at the same location, and that matters. Okay, now likewise, we can show that we've got L is equal to L naught over gamma B under the same principles of using 213A. Okay, and we can go through that. 213A is just going to say that X is equal to gamma B X prime plus gamma VT. And that's where we're saying that in terms of time that you have two different locations. So in other words, let's say that we've got Anna flying by on her flying skateboard that's going this direction, and I ask Kyle to help me out. We've got synchronized stopwatches, and I say, okay, at 10 seconds, record the position of her spacecraft. And so we both at the exact same time, in our reference frame, record two locations. In that case, he's going to say, hey, I saw the back of the spacecraft at this point, at the same time I saw the front of the spacecraft. Now, and since it's in the same time, what's going to end up happening is we're going to see a different length. Now, this is the same idea as the plane landing into the hangar. So the question becomes, is if we're going to see a different length, are we going to see her plane as shorter or longer? always shorter. Okay? And today is going to get really confusing because we're going to show from Anna's point of view how she's going to see the hanger as shorter. Simultaneously, both of these things are true.
I thought this was already confusing.
What?
I thought this was already confusing.
It's going to get worse. It's about to get worse.
I'm glad you found me.
All right, so this is the length contraction, and this is our time dilation. These two equations are really handy to use in the event that, like I said here, that we're dealing with something at the exact same time within a reference frame, here at the exact same location within a reference frame. Now, in the event that it isn't, that isn't a problem. You can still relate events. You just need to use the full 212 and 213 equations, A and B. So on your next test, you will have all four of these equations, and you will have these two equations. And of course, you have an equation for gamma V as well, if you haven't already memorized it. Once you start doing homework on this a day or two, you'll have that memorized very quickly. All right, so I think that's where we ended up with. And then I asked you guys to read through example 2.2, which we're not going to talk about, and I'm going to assume that you know what's in there. So, yeah, hopefully, I don't think there's too much in there that you're missing out on. So, it explains a little bit more. But okay, so, what do we define as an event?
Snapshot time.
That's a little bit of a dangerous definition.
Same place at a certain time?
Same place and same time. Okay. So in other words, if I'm, even though I'm moving by, let's say that, I don't know, I'm watching something, I don't know, what's a great example of this? I'm watching an explosion. There we go. I've put a firecracker in my hand and I'm about to watch it explode off. Okay. A closed fist for a little firecracker. It's going to go boom. All right, so Jared is flying by. Jared's on his super skateboard. He's going by. As he's right in front of me, looking right at this, and we see this explosion happen, that would be an event. Same location, same time. We have to agree upon events. All events have to be agreed upon. So even though here in a minute we're going to show that I think that something happens sooner or later, what's going to happen is I'm going to look at Jared's watch and say, Jared, your watch is wrong. I see that it says 1 o'clock, but it's really only 12:50. So agree upon the event. You think it happened at 1 o'clock, and I'm even looking at your watch, and I will say that I agree with you that your watch says 1 o'clock. But from my point of view, of course, it's only 12:50.
Wait, would David actually be that great?
Because I'm
Depends on how fast you're
Because
going.
I'm going that fast.
Because you're going that fast. And in fact, it would actually be the opposite case. You would see it just slower, so you'd see this 12:45 or something. But the point being is you have to agree upon events. I can't say that my hand exploded and Jared says, no, it didn't. Okay, you can't say that this didn't happen. Things like that. Or if we're saying, and the best example is two things happening at the same time. So if we have two birds that are flying at each other at relativistic speeds, very fast birds, okay, and they collide at a certain location, okay, that collision happened. That is an event. Jared can't come to the math and say, well, no, this one was moving faster, so this would dodge that one and something happened. No. That's an event. That happened. We all have to agree upon that. And all the physics and all the math has to back that up and going backwards. So even if you're coming at different angles, in other words, if you were to do the length contraction and time dilation, you can't just say that, one bird phased through the other one. No, that's not going to work. So, all right. Point being is that although events must be agreed upon, the reasons can differ. So in example 2.2 for the mu1, it says that there's length contraction. In example 2.2, the idea is that the mu1 should not have been able to make it to Earth. It's about 3 kilometers down, and it only has a half-life or a radioactive decay life of about 2.2 microseconds. How the hell did it get down there? Well, from its point of view, Earth was only 500 meters away. It actually sees it as length contraction, because it sees itself as not moving, and it sees that the space in between is much shorter. Just like Anna, moving in her very, very fast spacecraft, saw that the garage was very, very short. And that's why she feels like she got through it so quickly. So from the mu1's point of view, it actually gets down to the Earth in the 2 microseconds, so it's still alive. That's how that happens. Now, from the observer's point of view, they see time dilation. So the guy who's looking up at the mu1 is looking at his watch and like, dude, mu1, your watch is fucked. And it went by like a tenth of what it should have when it gets down, actually specifically a fifth. So for every second that passed by, or every 5 seconds that literally passed by, you're watching the mu1's watch, and it's only going by a second at a time. Okay, so you watch it, and like the mu1 gets down the bottom and says, hey, only 2.2 microseconds passed. I'm like, yeah, I saw that on your watch and all, but no. Okay, and then when it gets down here, it abruptly dies. Okay, so all of this is leading us to example 2.3. So we're going to go through 2 examples today, and that's really all we're going to get through. Because this example, second example, 2.4, is a doozy. And it will take a while to explain. Let's start off with 2.3. A proposed plane would carry intercontinental travelers, speeds many times of today's fastest airliners. Imagine such a plane that is 50 meters long when parked. All right, so whenever we have something like that, we start off with L0, 50 meters. This is the measurement of the object within its own reference frame when it is not moving. Okay, that's what you always want to think about for time 0, L0, etc. Okay, 50 meters when it's not moving, everybody agrees upon that. That's within that reference frame that says, even if it was moving, anybody that's moving at the same speed as the object that's moving will also represent that as L0. In other words, when Anna is moving at 0.6 speed of light, if she goes and measures from a plane, she's still going to see it as 50 meters because she's within that reference frame. Okay, so hey, anybody know what the length of a Boeing 747 is?
747 meters?
No, 747 meters. That's a full kilometer long. That is a big plane.
747 feet.
No, actually, I'm not sure what that indicates. No, it's closer. I'm not sure how many feet, but it's about 7 meters. I looked this up earlier because I was just curious as to how long this plane was. If it was a lot longer or shorter. It's a little bit shorter, but it's kind of moving fast. Okay, according to this, we're going to take it as its velocity here is equal to 13,400 miles per hour.
So that's the plane.
Yeah, which, is 6,000 meters per second. This is the plane. Okay, and we can say that this is also equal to, Mach 18. So a slight upgrade from the planes that we standardly deal with. So the plane is moving at 18 times the speed of light. It is cruising. So clearly much faster than anything that actually exists.
You always say the speed of light instead of speed of sound.
Do I really? Did I do it again?
Yeah.
Damn. 18 times the speed of sound. Shoot. That would be a lot faster.
Speed of light.
What?
18 times speed of light. How many laws of physics could be breaking that?
All of it. Okay. Off goes this plane. So we're going to start off and we're going to say that this plane is in LA, and I'm going to point north sideways because it's easier to draw it like this. And then we're going to say that it gets to Seattle a little later. Okay, so we have our person that's standing here, that's sleeping on his arm like this. And he's looking at this plane as it goes by with square nose, not terribly aerodynamic. And he's looking up into the window, okay? He sees a little passenger sitting here, and there he is, and he sees his watch. And he looks at his watch, and right when this happens, they're saying that both of their watches are exactly at noon. By the way, next Tuesday is Apple's big announcement. And then we could just cancel class and sit here and watch it. It's a live stream and from like 2 till 4, so.
Good one.
Apple's announcement
You brought
for
the
iWatch,
class.
the new phones, the new iPad.
Sure, we can cancel class.
See, there you go.
I'll sit here watching Upward Station for an hour for 2 minutes.
Cancel class to watch the news. So both of them have the same time being done.
Okay, at that point. So basically what we're saying at this point is when we're setting our origins to be equal. And we're going to run from here. Okay, so the 2 clocks are aligned. We're going to call noon the crossing of the origins. So, first, from this guy's point of view down here, A, how long is the plane? Okay, that's the first thing we want to solve, as this plane is going by. Okay, so, to figure that out, the question becomes, do we have to use the full equation? So we've got equation, if we flip back in our book, we can either use the equation 213a, okay, which tells us our position, and we can do it for the 2 different coordinates, x2 minus x1 is equal to gamma v, x prime 1 x plus v t, blah, blah, blah. Do we have to use the full equation, or can we use length contraction and y?
I feel like we can use the length contraction one.
Why?
I'm trying to weird out.
Yeah, that's what we're solving for.
I don't know, I just feel like because it's a hard moving object, it's going to get instantly, and I feel like putting it.
It all comes down to how we want to measure it. Okay? It depends on how we want to measure this. The first way we can measure this is say, okay, Bob can stand here, and Bob Jr. can stand here, and they measure these both at the exact same time. Okay, and then they can figure out the time dilation that changes for up there, and they get some sort of length. We have to use the full equations for that. Or alternatively, what we can do is we can stand here and watch when the nose passes us, and then a little bit later watch when the tail passes us at this location. Now, that's the important part. Now we've taken two measurements at the exact same location separated by time. That's awesome. Now we can use length contraction if we've done that. Okay? It's kind of a screwy way to measure things, but it works really well in special relativity because we use the simple equation. Yeah. So the idea being is I can use a measurement. I can measure how long something is crossing right now.
Okay.
So, yeah.
So like I'm running past you.
Right.
So I just got a 2x4 I'm holding.
Perfect.
Time it when it starts when I hit you.
Right. And so I'm timing it, and then I time it when it ends, and I take your speed that you're moving relative to me, and then from that I calculate how long that is. If that's the case, and I was not moving, I was taking the measurement right here, and then right here again, then I can use length contraction, because I'm taking it at the same location.
Now what makes you need to use the other one?
The other one, if I wanted to instead, in a time frame, so I'm going to have him, and then I'm going to have Cody stand over here and measure the back of it at the exact same time. So we have the same time, we have two different coordinates. We have to measure them as two different events, because they are two different events, they're separated, and then we have to subtract the two. Still gives us the right answer. So it's not going to be wrong, it's just more time consuming.
So in that case, we'd be using like x and x prime, the two different measurements.
X and, for the two different, no, x, so it's a good question. So I'm going to be using x1 and x2. That I'm going to be comparing them against the x2 prime and the x1 prime. So I have to set this up from their point of view. x2 prime minus x1 prime is necessarily the length of the object. Because x2 prime and x1 prime, in Jared's point of view, as he's running by, is the length of the 2x4, which is the 8 feet that it normally is. So to figure out x1 prime minus x2 prime, I have to sit here and figure out how long in time that it, the time difference between the two events. Does that make sense? Okay. But in this case, we can take length contraction, and we can do the easy way. So, length contraction tells us that I can say that the length of this object is L0 divided by gamma. Okay. Now, does this mean that the observer is necessarily going to see the object as bigger or smaller? Smaller. It has to be smaller, because gamma b, well, what are the ranges on gamma b? 1 and north of 1. But the second you even get to 1.25, we're already moving at fractions of the speed of light. Gamma does not change that much. We're going to see a gamma of 2 today. Holy crap, that's going to be fast. Okay, so gamma doesn't change a whole lot. All right, so gamma b. That's what we need to know, and we can calculate gamma b using the velocity over here. So gamma b is equal to 1 over the square root of 1 minus b squared over c squared. So if we put this back in the equation, we can write this as the square root of 1 minus b squared over c squared. So we just get rid of the 1 over that we doubly did. Okay, so this equals 50 meters. Okay, to the square root of 1 minus what we have is 6,000 squared divided by 3 times 10 to the 8 meters per second squared. Put our units in there, we're good little physicists. We'll be happy with that. All right, so who's got their calculator? Start bringing your calculators too, so we can. They don't just pick on Jared all the time from the calculations.
Mine's all the way back.
I'm working on getting mine sent back down.
Alright. Put this in your calculator. And of course, the easiest way to do this in terms of the calculator, it's the only reason I'm leaving units off. Make sure you're in degrees.
I got really close to 1.
With the whole thing you guys really close to 1 or just the thing in parentheses?
Oh, just, okay, hold on. So I got like 49.9999.
Okay, so, and does it actually kick that back out to you? Okay, so basically we get 50 back. Okay, that wasn't very useful. And the reason being is without a calculator with extreme precision, we're not going to get anything different than that. The calculator will acknowledge something slightly less than this, but it is too small of a number to be able to actually calculate this way. So we can use our binomial approximation. This is the reason I like this example. You guys haven't seen this before. Go over it. And I'm probably off the board here, aren't I? You know. Come with the camera. All right, binomial expansion. So when x is much less than 1, now what in this case am I saying is much, much less than 1? There's one quantity that's considerably smaller than 1 that's screwing all this up.
B squared divided by C squared.
B squared divided by C squared. That is our quantity at a time. So we've got B squared over C squared is incredibly small. Right. So we satisfy that. That's our situation. Binomial approximation says that 1 plus x to the a power is roughly equal to 1 plus ax. And for values that are much smaller, this is a really, really accurate approximation. Alright. Perfect. So, in our equation, what do we have here?
Let's say alpha x.
Ax.
That's
1 plus x to the a is equal to 1 plus ax. That's binomial approximation. So, for our example, what do we have here? We have 1 plus a negative b squared over c squared.
What did you call that? A binomial?
Approximation. I always confuse the statements binomial approximation with binomial expansion.
So there'll be rules when we're allowed to use this and not allowed to use this.
Just when this is really tiny.
Okay.
When you get an answer that gives you back the same thing that you had in the first place, then you know. The times I'm going to use this, all right, so that's a decent question. What are we going to do this? We're trying to deal with relativistic speeds that aren't really relativistic. We're going to find out here in a little while Mach 18 is freaking grandma slow in terms of special relativity. And that's the reason that we have to use this. When we start getting up to decent fractions of the speed of light, like 0.1, everything's useful once we get to about 0.1 the speed of light. We don't have to do this stuff. It's when we're trying to compare something that's relatively real world, which even Mach 18 isn't. Mach 18 falls right in between the category of shit we're used to seeing, stuff we're talking about, and we're trying to speed it up and still saying it's not into that category of the extreme.
So unless we're going close to 1 million meters per second, we're going to be doing this.
Pretty much, yeah. Yeah, and the million is actually a pretty good example of that, because you're thinking that speed of light is 3.8, so you got 300 million. So when you're around 1, you're getting closer to 1% to 0.03%. So it's actually a very good number to pick. So you want to be going about 1 million meters per second before you don't have to do this. All right, so this is our situation here. We've got 1 plus a negative. Now what I've done is I've included the negative in here just so that we can have all this show up. And I can say that, all right, that means I'll go 1 minus 1/2 times the quantity b squared over c squared. And I can calculate this, okay? I can calculate this. So, this quantity I can now put back over to here, and I can say that L is now going to be equal to the 50 meters times the quantity 1 minus 1/2 v squared over c squared. Now, multiplying this through, we're going to have 50, so let's not worry about that calculation. So it's going to be 50 minus what? What is this number multiplied by the 50?
That's 3 times 10 to the negative 10.
There you go. So, we're going to end up with 2 times 10 to the minus 10, or 20 nanometers. And this is the point, and this is the reason your calculator can't see this, because it's saying, over here I've got 50 point, and then I've got all the zeros all the way out here, and then I'm going to say, you know, it's actually going to be 49, all the 9s out here, and then down here at the very end it's going to be 8. It's a little bit harder to see. So if you do it this way, you'd say, okay, 20 nanometers, which is a very good approximation.
So nobody's going to see the difference.
No, nobody's going to measure on a 50-meter longer plane. I'm like, ha, look at that plane. It's 20 nanometers shorter than it was when it was moving. No, you're not going to see that at all. What you got?
Where'd you get the 1/2?
The 1/2 is my A value. So we have this to the 1/2 power here, which is my exponent because it was square root. And then so I take that as my A power and throw it in front of you. Okay. All right. Now part B in that. Later in Seattle, 1,600 kilometers north. What did I still on here? Nope, I'm not. Later in Seattle, 1,600 kilometers north. How does the ground observer differ from the plane's watch? Oh, okay, right. So we've got 2 people that are recording this. Okay, from his point of view, we want to know what his watch says right here versus the plane when it gets here. What does the watch up here say? You know, when it says something completely different, it's still square nose plane.
That's the reason I don't go very fast.
Say again?
That's the reason I don't go very fast.
Because it's got square nose, yeah. It's only going to Mach 18. It could do so much better. Okay, so now, is this guy's watch synchronized with this guy's watch? Why or why not?
Has to be. Right.
Why?
Because of the
Yes.
same reference.
Same reference frame. Okay. So, well, we're assuming this guy taking his watch is the equivalent of this guy, you know, just magically being here or seeing what's going on here. Anything that's within the same reference frame, we say that all the watches are synchronized. There can't be time dilation within the same reference frame, okay, or length contraction. So later on, once we get the stopwatch, then we'll walk towards the center and discuss how long that took for the plane to go from here to there. All right, so first thing we need to do is we need to figure out what his, if we're going to say that the difference between these two, this is happening at this location, I can say, okay, the change in time is equal to the gamma v times the change in t0. And I can figure out the length contraction. Now, it's using this time dilation equation. What is this change in time and what is this change in time? The difficulty in this class is not the equations. None of these equations are terribly difficult. It's figuring out what do you plug into what. So that's what I'm going to try to stress. What is delta t0 in this and what is delta t? Plane flies overhead, gets here.
Delta T, the Bob and Dude in Seattle.
Bob and Dude in Seattle. Yes, Bob and Bob Jr. Okay. Why? Why is the easier one to figure out is actually the delta t0. Why is the delta t0 inside the plane?
Because that's what's going fast. That's what we're trying to solve.
None of the above, because we could really think of the plane as standing still and Earth spinning underneath it. What does time dilation require?
Change speeds. Like horribly different.
No,
Change in relative speeds.
We can use time dilation instead of one of the big equations on 212 or 213 if what?
One object's going really fast and the other one's going really.
No, it has nothing to do with the velocity with respect to the two of them.
Bob another time, like, separate from the reference.
Nope. Has to do with position.
If they're in different positions?
If they're what?
If they're in different positions?
If it's in the same position. Time dilation only works is if the measurement in one of the reference frames is taken in the exact same position. Okay, that's how you can confer it. So now here's the confusing part. Like, what do you mean? Nothing's in the same position here. From the guy who's watching on the plane, it is the same position. I am just sitting here watching my watch. The Earth is spinning out from underneath me, and then I look at my watch again later on. A certain amount of time has passed. I have not moved. In my reference frame, x is still 0, right from here. Okay, these are the type of questions you got to start getting used to asking yourself when you can do things like that. Okay, so that's the time you can use time dilation. Now, if you can identify that one of the measurements was made like that, and we can with the watch, we can say, all right, that's time 0 up there. All right, great, let's go ahead and solve for delta t. Problem is, we don't know how much time has passed up there. They haven't told us that. In fact, it's going to be easier to calculate the amount of time that's passed down here. How am I going to calculate the amount of time that's passed down here from the plane to go from there to there?
Well, I'm just gonna know how far LA is from Seattle.
Simple velocity equation. Basic, classic mechanics. I can say that the velocity in the x direction is the change in x over the change in t. In this case, change in t is going to equal my change in x over the velocity, which is equal to the 1600 times 10 to the third meters, because it's in kilometers, divided by velocity, which is 6,000 meters per second. Okay, lots of questions. For starters, why can I use the classical equation here? Why am I in danger of using it elsewhere? Why can I use it here?
Because you're just talking about one reference point.
Everything is within one reference frame, so we can still use Newtonian physics. From our viewpoint, what happened with the plane, everything is in there. The other thing that you'll notice is I put V over here. I didn't put U. Okay, why am I using V instead of U? You guys remember the difference between the two? The difference is important.
The V is the velocity between the two reference frames, not the
Correct.
reference frames.
Okay, so what does U represent?
The velocity of the person in their own reference frame.
No, not necessarily. The velocity of an object within that reference frame. In other words, if this lady up here was to throw a baseball, and we wanted to talk about how fast she saw it versus how fast this person saw it. If they're not moving, then their velocity is the origin, it is the reference frame velocity. Now the next question is, when we throw an object up here, we've got U prime from her point of view and U down here. We're going to see that as moving as two different speeds, etc. Okay, my question to you is, why do I look at this as V, and why does he look at me as moving negative V the other direction? Why is there not, like, I'm about to calculate this using classical mechanics, using just the velocity of the plane. I'm saying the plane's moving at this. Does the plane think it's moving at a different speed, at a different velocity? Or does it think it's moving at the same velocity?
Well, I'm pretty sure its speed is going to be still the same, right?
Has to be. It has to be. Because the point being is, if I'm moving past you, Dave, at 10 miles per hour, whether you agree that I'm the one doing the moving or you're doing the moving, you have to see the same separation. You have to see yourself going 10 miles per hour that direction.
The acceleration is a whole effect, right?
Yeah, well, there'd be a lot of issues, yeah. So the point being is that the velocity between reference frames, it's the one thing that's always constant. There's no time dilation or length contraction for the velocity between reference frames. That's constant. So it's really handy that from our point of view, within this reference frame, we can go ahead and use the classical mechanics point of view that says they're moving at this velocity up there. Now that plane up there is going to say, I am moving at that velocity. I see the velocity of the Earth moving out from underneath me. I'm just going to see time go by slower. Okay? That all of a sudden time is not taking as long for me to get there. And all of a sudden I'm there faster, if you will.
Wait.
And we'll see that in a second.
So wait, if time's going by, if time's going by slower if time's going by slower person plane, wouldn't they think that they're going at speed then?
No, because then what is the other choice that they have to see? Perfect question. If time from their point of view is going by slower, and we'll calculate that by how much, and it's going to be a stupid small amount. And they also agree that they're going 6,000 meters per
It's going to
second.
take them a while to get there. I know.
No?
Doesn't
They're
seem
going
like
to
travel is
get there
fast.
sooner, right?
Okay, so Kyle's got it. So they don't think they're going as far, which is to say what? Length contraction. They see the distance between LA and Seattle being smaller than the 1,600 kilometers.
So then that accounts for the difference in time.
And again, this gets back to the idea that the events, they're going to get there, they're both going to agree that they got there at the end. And then from the guy's point of view on the plane, they didn't go 1,600 kilometers, they went something less than that. Like 1,500, or in this case it's going to be 1,599.99999, whatever. Point being is that they went less. And that's how they got there at a sooner time. From down here, of course I'm going to say this is 1,600 kilometers, and we're going to say that you have time dilation and your watches are just wrong and they run slow when you get there. Again, same result, but the two different points of view. One says length contraction, one says time dilation.
So what happens if there is acceleration?
We don't do that.
Is that quantum?
No, it's not. It's not that you can't do this, but take all of the simple velocity equations. You remember we learned in the first couple chapters of the first chapter of physics, right? Algebra-based or calculus. We have one chapter of here's velocity. If you're going at a constant velocity, how far will you be in 10 minutes? That is all we're dealing with right now. And we're going to be dealing with this for like 4 weeks just trying to understand this. Then try accelerating.
No.
It works. Everything works in this. But if we can't get a good mental grasp on just constant velocity, trying to go on acceleration, you just be blindly like, I don't know, I'm going to put numbers in an equation. It's going to give me an answer. I won't know what it means anyway, so I'll just hope that it's right. At least if we're dealing with the constant velocity, we have a prayer of understanding what's going on. Because whether or not you guys can use the equation, I'm hoping that you'll kind of get a feel for this stuff. Does that make any sense?
That makes sense.
Nothing changes. It just gets a lot more complicated.
So we're not doing acceleration this semester.
No. And you don't ever want to deal with acceleration if you can avoid it, because it gets messy. Okay. So, what was I going to say about that? Oh, so we got to figure out how long this is. 1,600 kilometers divided by the 6,000 meters per second. I'm getting an answer of 266.66666 blah 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 seconds. So we can go 267 seconds is how long we see this taking. All right, from our point of view. So now, using the time dilation equation, which we can use because from their point of view, they're at the same location. We can say that.
So it's up 4.5 minutes.
Yeah, how awesome is that? Approximately 4.5 minute flight, all the way from LA to Seattle. I want to be on this plane. So we're going to find out that's not very relativistic, but it's freaking convenient for travel. It's very, very handy.
Hey, you might be realistic one day.
So what?
Can be realistic one day.
Yeah. Here's the problem. It can't be, but I'll explain why. Anytime people want to talk about the speed of travel, there is a limitation. And I don't know if I told you guys this before, but it's your abilities to handle your body's ability to handle g-forces. Because here's the thing: if you're going, I don't care where you're going on the Earth. If you're going from point A to point B and you want to get there, you can go. Your body can handle a maximum velocity of infinity. Well, velocity though, infinity. It doesn't care. Your body can't tell relative motion. I mean, we're on this giant spinning ball of death, and we can't tell. You can go as fast as you want. What your body has a limit to is the acceleration. So let's say that this is your maximum velocity. You're going to have some sort of acceleration up like this and some sort of acceleration down. This maximum velocity that you can achieve is simply based on the acceleration you can handle. I, for a fact, know that I can't handle over 4 Gs. And I know some of you guys have heard that story where I passed out in the airplane. My friend of mine does, he's a glider pilot. He goes, let's find out where you pass out. And we did. That passed right out.
So what's his limit?
It's considerably higher because he's trained himself. He's gone through, and then I'm not sure what his limit is. I could actually ask him. You can send me an email and ask him. But higher than that, hopefully considerably higher than that, so he doesn't pass out too. But you can get special suits that actually squeeze your legs. Yeah, it's so in the Air Force, what they do is they have these pressurized suits that push the blood all the way up so that you can't have any blood in your feet. Because if you start to get these G-forces, all your blood rushes down. And they're trying to keep the blood in your head. Why do you pass out in the first place? Because basically you're like, a sand globe or something, and all the blood goes flowing on your head. You're like, there's going to be blood in your head. That's why you pass out. 4.2 or something like that. 4 point something, thank you very much. Congratulations. Definitely less than 4.5.
And then we have physics.
So, the reason being, so then even say that you didn't care if you passed out. Let's say that you were awesome and you just want to handle 5 Gs and be passed out the whole freaking time. And have to be resuscitated at the other side, I suppose. You might actually have brain damage if you didn't have blood in your head for that long. Point being is that would limit how fast you can move. And I'm going to guess it's going to be a lot less than 18 minutes.
So, even with a slow acceleration over time, you still feel the same amount of Gs?
No. The acceleration is the amount of g's that you feel. It's the amount that you're changing speed with respect to time. So we normally feel 9.8 g's. We're actually used to a certain acceleration. You don't realize it, but I mean, we're being pulled down to the Earth because as the Earth is spinning, gravity is pulling us down. We're used to a true rate of 9.8 g's. We are on a giant Ferris wheel that's spinning around. And we're just so accustomed to it being pulled down like this, we never think about it. The only time we think about it, and you say, oh, I don't really feel like I'm being pulled anywhere, it's not a big deal. Okay, spend a day on your head. Like, literally invert yourself and tell you that you don't feel the force. It's going to become real uncomfortable really fast. Because now you're feeling that same force, but you're upright. It's going to be the exact opposite, and all the blood's going to rush to your head, and you're going to have a really bad day.
Did that happen to you?
Say again?
Did something happen to you with your neck and
Yeah.
Yeah.
That's right, too? Oh,
No, I think there's Cody told me.
Yeah, this is just, so I'm trying to do the whole CrossFit thing, and I got a good buddy of mine who's way better than I do. So he's got me doing vertical push-ups, which was fine and all. But I'm doing this, and they're making fun of me, of course, because I'm not doing it fast enough. And so I'm laughing, I'm sitting there with all my weight on my head, upside down like this, I'm laughing, and then I turn my head and went, oops. And I pulled something in the back of my neck, so I was all messed up for 2 weeks. Yeah, good story. Anyways, back to this. LA to Seattle in 4.5 minutes. What were we doing? We got lots of stuff to do. Oh, now we can figure out this time dilation bit. Alright, so delta T0 is going to be equal to that time divided by our gamma V. And we got to calculate what our gamma V is. Okay, so if you remember, we already calculated what gamma V was a second ago. I'm going to erase all this. We said a minute ago that gamma V was this quantity 1 minus 2.0 times 10 to the minus 10th. Or actually, no. It was, isn't it minus 1 times 10 to the 8th?
There was 20 nanometers. So I
That's
think
2 hours.
Yeah, but that was after we multiplied by the 50. Oh, that was after we multiplied by the 50. Come on that. Let me make sure I got this right.
yeah, 2 times 10 and then that was right.
2 times 10 to the negative 10. Okay, good deal. Alright, so this is our gamma V. So if we plug this in and we calculate what our change in time naught is going to be, we can simply multiply by this. We're going to find out that we get 266.6666 seconds again, minus 5 times 10 to the negative 8 seconds, or, roughly 50 nanoseconds. Okay, so 50 nanoseconds, or I think it was 53, but in any
What
case.
happened with the algebra was, we just plug that in there.
Right here. So we want to now know what, we calculated this because we can do that in classical terms, and we want to know this. So just move that around and multiply by the 2.6, or the 267 seconds. And then we figure out the fraction of it.
Is
So that's
that
only
to the
the-
negative 1, I think?
Yes, to the negative 1, because it goes underneath. So, but the problem is when we multiply, we can just take this and multiply by this quantity, and then we get rid of the negative 1.
Okay.
Sorry, I kind of rushed it there. Alright, so we're not seeing a huge time difference. We're not seeing a huge length difference. We're talking 20 nanometers and 50 nanoseconds. Nevertheless, there is ever so slightly a difference in this. Okay, and we learned how to use the binomial approximation. So that's fun. All we've gone over is example. We're literally in class, we're doing 2 examples.
Maybe 2.
We better get through. Yeah, maybe 2 at this point. Rawr. Okay.
Let's hear another story.
No!
So I'm going to do a lot of stories when I watch this.
I don't think so. Like,
Just a couple random tangents.
couple tangents, yeah. You can be known for those.
From your notes,
Well, yes, actually, my notes are already uploaded on Blackboard. Did you find them the first set?
No, for today.
They will be.
That's fine.
Yeah. So, what you guys will notice that I'm starting to, all of my chicken scratch, which I don't know if you guys can read it anyways, but I'm happy to put it up there. I'm starting to PDF these, and they'll go up on Blackboard as well. So they'll just say the lecture number and the notes. So, I don't write that you guys will necessarily read this, but if it does help to go back and look at it, feel free. Okay. So, now, back to Anna and Bob. All right, example 2-4. Coup de grace of special relativity examples. Idea here, we've got two spacecrafts that both have a length, which the book chooses this is really weird. This is kind of they both have a rest length, L, of 12 times root 3, which is roughly 21 meters. It's actually 20.6, something like that. They say that it makes the math easier. I think they're silly. But we're going to go with it anyway. This is the length of the spacecraft, so they're both the same length, 21 meters. Okay, now, the way that this is working is we've got two spacecraft. Okay, we'll show one of them right here. Okay, so two spacecraft. Now, on each spacecraft, they have a clock here, the front, the middle, and the back. And there's going to be another one that's going by as well. Now, the ones, Anna's spacecraft, you can look at this two different directions. Anna's spacecraft is either moving faster than Bob's by a difference of v, which we'll talk about here in a second, or Bob's spacecraft is going backwards relative to Anna at v. Makes a little bit more sense to say that Anna's is going faster, although there is no actual mathematical evidence. If that's the case, if Bob sees Anna's spacecraft going faster as the spacecraft goes by, we're going to see Anna's spacecraft as smaller or larger. Is Bob going to see her spacecraft as smaller or larger? Small. Small. Again, it always gets to the idea of length contraction, and not length expansion. Boy, that's scary. You know, it's kind of interesting just from a philosophical point of view. Special relativity is kind of nice because it talks about time dilation. Quiet. Time dilation and length contraction. The point being is the closer we get to the speed of light, the farther we can actually go. What if it was the other way around? What if it was time expansion and length expansion? In other words, the faster we went, the farther distances were, the faster time went by. So the faster we went, the quicker we'd age and die, things like that.
You get like,
Well, but the point being is just think about how depressing that is. The idea being is that we really want to try and get to another planet, so we'll go faster, but that means that it's going to be further away, take us longer to get there.
So
You would
let's
literally
just go
find
1 mile an hour and get there 2 seconds. You'll be flying to your death.
Yeah, very quickly. And you would age quickly and die within
actually,
years.
you're never get there though then.
And you would never get there either. That's my point about being depressing. Special relativity actually gives us hope that says the closer we get to the speed of light, the closer distances get anyways in the first place. And you guys got a problem on your homework that you'll go through. Make sure you grab one of these before you go. So that we actually have the ability to get anywhere in space if we can go fast enough. So I think that's kind of neat. Definitely a more positive point of view. All right, back to this. See, those are
So it's like on Star Wars when you go speed up, like the lights like drag back, then they
Kind
zoom
of.
back in front of you like super quick. Like
That's actually not that far off. It really isn't from what, if you could view this stuff, what you would more or less see. Because we're going to show here in a little bit that we're going to see these two spacecrafts and they're going to have different times and they're going to be seeing each other just across the spacecraft even. Okay, so now we're going to define an event here. Oh, I really should have lined this up there. This is Anna, and we've got Bob down. Now, we are going to align an event here, right off the bat, right here, event 3. Okay, where the back of the spacecraft line up. I really don't know why they call it event 3, but that's the one we start with. Event 3 is when t equals 0 seconds. Both clocks read 0 when the back of the two spacecraft line up. Okay, so now the question is, although that's true, from Bob's point of view, when the back of his spacecraft says 0, what do the rest of his clocks say? From Bob's point of view.
more than 0.
No.
No, they all say 0.
They'll say 0. Now, from Amanda's point of view, if the back of her clock says 0, what do the rest of her clocks say? No, from her point of view, they also say 0. Within your own reference frame, everything has to align. Okay. But now here's the weird thing. Okay, that is true. That is 100% true. But when Bob's looking at Anna's other clocks, he goes, no, your other clocks are wrong though. And they progressively get more wrong the farther you are in the spacecraft. And Anna's saying the same thing about Bob's clocks. So what we're going to do is we're going to solve everything from Bob's point of view first, and then we're going to look at Anna's point of view.
Is Anna's and Bob's other two back in time or forward
we will see that. Oh, wait, ask that again.
From Anna looking at Bob's clock, the one in the front of the plane, is it back in time?
No, because Bob's moving slower.
Yeah.
Bob's moving slower from her point of view, so she's going to see that his clock is farther ahead in time, and her clock is actually going to read it sooner, which is going to be a little weird. Okay, so we got 0 seconds here. So Bob says that this is an event, this is where the clocks are aligned. We can only have one event where the clocks are aligned, which means that the rest of these clocks don't necessarily say 0 seconds from Bob's point of view. Now, why don't they? Because these are different events. What makes them different events? They're the same time from Bob's point of view,
But they're different places.
different locations. So the second, we're saying that this is one location. Now you could have said anything like this. We could have set it up that Bob is aligned these two to 0. It doesn't have to be necessarily right here. We're just picking a place and it makes sense to pick a vertical spot that we can set them to be 0. But the second that any place off from that position that we're saying that they're aligned, then would it be a different place, therefore a different event, so the clocks are going to read differently. All right, so the question now is, we're choosing this one, but we want to know this clock and this clock. What do those two clocks say? Okay. Ooh. We're on page 2 of 6 pages. That's what we get through today. It's not going to happen. All right, so how fast is Anna moving? Now, Bob specifically sees Anna's plane move exactly half the size of his. Now, at rest length, we know that they're supposed to be the exact same spacecraft. One is just moving faster than the other. Okay? So, right off the bat, if that is true, what can I say about gamma? What do I know that gamma V must equal, and why? 2. Because right off the bat, we can say that L is equal to L naught divided by gamma V. Okay, so the rest length of Anna's ship is L0, but he's seeing it as half that, which must mean from what he's seeing, it's L0 divided by 2. Gamma V must be equal to 2. So this is the largest gamma we've ever dealt with. If you remember, up till now, we had a gamma of 1.5. So the question becomes, why did I care to use this? Because just by the fact that Bob sees Anna's spacecraft as half the length it normally is, we can calculate Anna's speed now, relative to Bob. Okay, so I can say that gamma V is equal to 1 over the square root of 1 minus v squared over c squared. And now I can set this equal to 2. All right, so let's do some algebra. So I've now got 1 minus v squared over c squared equals 1 squared. See if all of that random math I just did made sense. Everybody follow that algebra? Yes. Okay. And then we do some more algebra, and we magically say that V is going to be equal to 0.866 c. So 86% the speed of light. Did you know that 51 divided by 60 is exactly 85% or 0.85? I was very bored on the way home. I have a specific reason why, though. I'll explain later. Okay. No, we got to finish this. Okay.
We're not going to finish this.
We are. We're going to try. We're not even going to get close to finishing this. We're not kidding.
So we should just stop now or we get all at once?
You got a good point.
No, we're not stopping now. No. All right. Shite. Like your homework is problematic. Okay, so we've got her moving at this velocity. Now, what's the next question it wants to know?
So that's velocity of Anna.
Velocity of Anna with respect to Bob. Now, you could look at this again. We could say that Anna's staying still and Bob's moving backwards at negative 8.66. Doesn't matter. It usually is easier to make everything go forward. So we got to make her go faster. Now, B, at t equals 0 seconds, what do Anna's clocks read according to Bob? So back to this question, what do these two clocks read? All right. So, good news is you probably aren't going to have to do any of those homework problems, maybe one of them.
So do we use trig to know how the distance was from the...
What do you mean? Oh, well, this is... Okay, so the question is, how far is this from here and how far is this from here? Like this? No, we're not going to necessarily do trig. What we can do is we can say that from this point of view, this is a position of L over 2. And remember, since we're moving in this, y and z don't affect anything. So if we're moving in this direction, this y coordinate doesn't affect anything. It's just the x coordinate that we care about, the x position. So we can now say that this is a length from here to here of L over 4.
Where did 4 come
Well, L over 4, L over 4, L over 4, L over 4 is the full length of the spaceship. L is the length of the spaceship.
from? Oh, and you just
divided by 4.
Just divide by 4, yeah. To get a quarter to figure out where that position is. Okay, so, first one. Let's go ahead and take this front clock right here. From his point of view, which is that clock read. Alright, well, we need to use one of those large equations. I think it's in 213. T prime per clock from his point of view. Now, to get information about per clock, we need to know his position and his reading of that time. It's a function of x and t. T prime is a function of x and t, whereas t is a function of x prime and t prime. We need to know both of these things.
So this is the one in the front of the plane?
The one on the front of the plane. We're going to do both, but let's go ahead and start with that. Okay, this has to be equal to gamma v times minus v over c squared x plus t. All right, so from Bob's point of view, what is the time? Zero. So this thing goes away. This is still 0 seconds right now. All right, so t prime now equals gamma v, which we said is 2. Okay. Now we've got minus v over c squared. So this is going to be a minus 0.866 divided by 3 times 10 to the 8th meters per second. So when this goes v over c squared, you still end up with that 1 c left over. So we take out one of the c's, which was the 8.66c, we still end up with 1 left over. And then we have to multiply by position. Now the position here is going to be L over 2. All right, so I'll just write this in as L over 2. And we'll run that calculation. Now, if you put that into your calculator, is this going to be a positive or negative number?
Could be negative.
It's going to be negative necessarily, right off the bat, which is a little confusing.
So,
All right, we're going to say that this is equal to negative 60 nanoseconds.
so where did the L over 2 come from? Like, I'm confused how you relate it to the...
From Bob's point of view, the x coordinate. Okay, so when we deal with coordinates and we're looking at stuff on here, we want to talk about positions, right?
Yeah.
We have our x coordinates, we have our y coordinates for this. Okay, we're going to assume that we're aligned to z. All right, so x and y. Y doesn't matter. Y prime will always equal y for everything. Z prime will always equal z. All right, so if I want to know about a time that's reading on one of her clocks, I need to know what the x position of the time is in my clock. So the x position for Bob, we're setting this right here. Actually, I should show my x's across here as being 0, 0 right there. So then my position of that clock, from Bob's point of view, is L over 2.
Okay.
But it's a good question, because obviously I didn't answer that well in my class. So we get minus 60 nanoseconds. Now, he's seeing this as a linear shift. He's not going to sit there and see one half of it larger than the other. I mean, when he looks at that, he's not going to see this thing as, I don't know, what would the extremes be? Fins on the back, or alternatively, you can see it as or the two extremes, where like the back end looks really, really big, and then it instantly comes up to a nose, or vice versa, where the whole thing is nose, and then the whole back of the spacecraft is right there. He's still going to see it linearly, so what can I immediately tell that that middle clock is going to be? Half, so negative 30 nanoseconds. 30 nanoseconds. Now, this is where it gets interesting. From his point of view, all of his clocks read 0. At this point, her clock, back clock reads 0, because that's where they synchronize them. He's looking at the other two clocks, and he's actually seeing them. And he's seeing that the other clocks are moving at a different time. Now, from her point of view, she's looking out, so Anna and all her buddies having a sleepover in their rocket. This buddy over here looks over the clock and sees that they both align with 0. Meanwhile, Anna, who's actually in the front, looks at her clock and says it's minus 60 nanoseconds. The experiment hasn't even started, and looking over and does see 0 over there and sees his clock. So they agree on all of these events. From Anna's point of view, this happens before she reads that one over here. This happens 60 nanoseconds in the past. The experiment hasn't even, Anna's saying that, wait, the experiment hasn't even started yet, and your clock's already reading 0. 60 nanoseconds go by, and then her buddy back of her rocket is saying, oh, I read 0 now, and so does he on the back of his ship. Anna's going to be looking at all of his clocks and seeing them differently as well. So, from when that happens, when Anna's standing in the front of the spacecraft looking across, 60 nanoseconds goes by, her buddy in the back says, hey, we're aligned, we both say 0 back here. What is Anna going to see Bob's clock read? Positive or negative? Positive, because some amount of time has gone by. Okay. Now the funny thing is, it's not going to read positive 60 nanoseconds, because Anna's not going to see that 60 nanoseconds went by in that amount of time. Is she going to see that as more or less? Yeah, when she looks across and she sees, now keep in mind she's passing, but when her clock gets to 0 and she looks across, what is she going to see?
Is it 120?
It's going to be a huge amount of time. Yeah, 120 nanoseconds. His clocks are just flying along as far as she can tell. They're moving along quite quickly. Okay.
It is 120 that she sees?
Yes, she should see that when it's across.
So
now,
the
problem
I've
is,
found that you can kind of use.
you can use these to put these together, right? But it's going to be a little bit difficult. Here's the problem, though. From her point of view, she won't see 120 nanoseconds in the Y.
She took time to get up the front plane.
No. Where will she be in position at that point? I guess we'll stop here. Okay. At the point, by the time her clock gets to 0, she thinks the whole experiment is ruined because she's already passed his plane. If the plane was long enough that she could see a clock cross and be at 120 seconds, but she will actually be considerably past that plane. Because from her point of view, is Bob's plane bigger or smaller? Smaller. From her point of view, she's staying still, Bob's plane's going backwards. She sees his plane as smaller, he sees her plane as smaller. So by the time 0 gets by, the plane's already gone, and she's well past it. She's twice the length of it, in fact, at that point. All right, we'll pick up on this. She's on page 3 of my notes. On Tuesday, so no homework. I'm going to leave these sheets, because I'll put them off and modify them for and maybe they'll actually say modern instead of modern. Tuesday. But your homework that I did give you guys on Tuesday, that is still due.
Yes, considering you taking out homework on Tuesday, even when it's on Thursday, would you prefer that or not? If you ever run out of homework a week from time to that?
Yes.
He's seriously taking everything we get to do on Tuesday. Would you have to prefer that?
What was the class consensus?
Just tell us your answer.
Very political way to
I
go
want
about
to
it.
know the class consensus first, because I'm obviously the decider.
No, you're actually
No,
not.
you're not.
Okay, good. I'm assuming it's still 1 week from the day it's due.
Yeah.
Okay.
Yeah, my reasoning behind that was that way if I was collecting your work on Tuesday, then I would always give it back to you on Tuesday. So whether you had work on Tuesday or Thursday, it'd still be due Tuesday. Because even today, you guys have 5 days till Tuesday, so it shouldn't be the end of the world. And I thought it'd be less confusing. Tuesday is the day for all things.
I was the only thing I'd like to say.
But I got outvoted, and that's fine. The original policy can stand. It's not that big of a deal.
As long as the dates are on the.
And, right.
You guys want the correct dates?
Which I didn't do that last time, but that hopefully will be.
So then, if you're in this class, you can probably not set it to whatever date.
Yeah, so we'll stick with the regular policy.
Okay.
And I'll give you guys back homework whenever I can, so it'll happen in random chunks.
Is it any better than what it was during that short break in companies? Look like special topics in physics.
It'll be about the same. Because this stuff takes a lot longer.
About a week worth of lessons.
Okay, the night before test.
Yeah, you do your homework before.
Hey, we're gonna let her entirely. No extra take home in that class. Tip to the bottom. That was a bad, that was a bad.
Yeah, well, have a good weekend, and we'll see you guys.
Yeah, I know physics.
Sir, when's Pumpkin Festival? I wanna go up there again.
I don't know, sort of, when's the third weekend in October?
Third week in October?
That's normally it.
Or when, in circle?
You should have modern physics, don't you? That's super cool.
Yes,
That's
that's
fun.
We can,
That's physics.
you tried that? No. Oh, no, gosh, no.
You went to the last report?
What?
You went to the last report?
Yeah, right. I got a question about the homework. Should I just go to your office? The day?
No, you can just bring it. Which one?
Well, I can't figure out C&E, it's like basic math with that.
See?
Let's go to a bit of modern.
I just walk out confused.
Okay. It's gonna be C is 2/8. Okay, so. Okay, so you've got this from your x prime is equal to ct prime. Okay, so you want to throw it right in here. So we have ct prime is equal to ax, bt, or x is equal to ct. So throw that into both of these equations to eliminate them. So you want to eliminate the x and the x primes in both equations. So where are you at right now with that?
I'll talk about that soon, but I never really that. I was writing quite a bit different areas in different places.
2 equals 2 prime minus c. So what happens here?
Those are just two different equations I solved. That basic equation for T.
Okay, well here, let's try that.
I thought this recording.
Oh, yeah.